Hello, friends. In the fourth lecture of combinatorial mathematics, we'll study about the equivalence relations, equivalence classes. In fact, I have already given you the clue regarding its utility in determining the exact number of partitions of a finite set. So, first of all, we give the definition of equivalence class example and the fundamental theorem of equivalence relations. So consider the set A, B, C, D, and let R be the equivalence relation defined on this set A. Then equivalence class of an element, because we see the equivalence class of an element, it is denoted by this kind of symbol, the square bracket x, and is defined as square bracket x, or the equivalence class of x, is consist of those elements of A such that x is related to y. So any element of an equivalence class may be chosen as a representative of the class, because in this class not only this x but several elements will be there. Suppose y is suppose some element t belongs to this, then we can also represent this class as a equivalence class of t. So these are the properties of equivalence class, and we can talk about equivalence class only when we are having an equivalence relation R on a set A. Then these are the properties. If R is the equivalence relation on a set A, then every element of X is a member of equivalence class. Every element X belongs to is a member of equivalence class A, right? Let xy are two elements. They are said to be equivalent. They are said to be equivalent if and only if they belong to the same equivalence class. Or in other words, for all xy belongs to A, x is related to y if and only if equivalence class of x is equal to equivalence class of y. Every two equivalence classes are either disjoint, and if they have something common, then everything will be common. That means they will be equal. So that means we can say either they are equal or they have nothing in common. Their intersection is empty. Now, the fundamental theorem of equivalence relation states that every equivalence relation on a set generates a partition of set, and precisely the partition into its equivalence classes. On the other hand, every partition of a set generates an equivalence relation on this set, right? So, how this theorem works, I try to explain with the help of an example. Suppose we have this set A, and already we have discussed it have five partitions. Suppose I consider this partition. In fact, this is the set A, and in this partition we are having two sets. That means this is one equivalence class. It is having two elements A and B, and this is another class which is having element C. So in fact, this set is A. This is an equivalence class. That means it gives you a relation that A is related to A, B is related to B, because equivalence relation is reflexive. It is symmetric also, so we can get this kind of situation here. A related to B, B related to A. And third element is not there, so we don't talk about that. And the second one gives you only one thing, that C related to C. Nothing else can be there. So in fact, this becomes an equivalence relation. Similarly, we can corresponding to this, we can develop an equivalence relation corresponding to this also. We can develop R2 because this is an equivalence relation. This is an also partition. So the three relations can be developed like this: fourth one from here and fifth one from here. So that means the number of equivalence relations that we can define on a set gives us the exact value of the number of partitions of a set. So this is the utility of the fundamental theorem of equivalence relations. Thank you.